Good afternoon to everybody. My name is Simone Quaranta, as you can grasp from the title. This afternoon we are going to talk about single chirality carbon nanotubes and their application to dye-sensitized solar cells. So everybody knows that single chirality carbon nanotubes possess different optical and electronic properties, and those properties are tunable. You can see here, you can see that the carbon nanotubes we separated in our lab possess different band gaps. So we were wondering if we can apply those properties, different band gaps and electronic conductivity, to photovoltaic devices, to increase the efficiency of photovoltaic devices. The kind of device that we choose as a preliminary test device is a dye-sensitized solar cell. Why we chose dye-sensitized solar cells? Not because we are trying to improve the efficiency or maximize the efficiency of a DSSC, not because we think that DSSC is the best device for application, but because all the processes involved in the mechanism of a dye-sensitized solar cell allow to test different properties, specific properties of chirality-separated carbon nanotubes. For example, everybody knows that carbon nanotubes are black, so they absorb the light and they compete with the dye for light absorption. So if we, instead of using mixed carbon nanotubes, we use the single chirality carbon nanotubes, we reduce the absorption to a broad band to specific absorption peaks. So the efficiency is supposed to be increased. Second, when we put in contact titanium dioxide and carbon nanotubes, a Schottky barrier is formed, so the recombination is reduced because electrons receive a push to the forward direction. Now, the height of the Schottky barrier height depends on the work function of carbon nanotubes. So by selecting the chirality, we select the work function of the carbon nanotubes. Last but not least, carbon nanotubes have a catalytic effect for the recombination of the electrons in titanium dioxide conduction band with the electrolyte, which is the reduction of the triiodide to iodide. So if we get rid of the metallic tubes, we can reduce this catalytic effect. The starting material are HIPCO tubes, so it means carbon nanotubes grown by high pressure carbon monoxide disproportion, and we characterize the material. First thing is the Raman spectra. As you can see, here, as you could see here, sorry. Here. The RBM band is comprised of very small diameter carbon nanotubes, semiconducting carbon nanotubes, in a small distribution, which is ideal for the separation of carbon nanotubes by shell chromatography, shell permeation chromatography. Of course, the price that we pay to the small diameter is that they decompose at pretty low temperature. They start degrading around 375, and thus restrict the thermal treatment of the photovoltaic. Another characterization, maybe the most important one, is the UV-Vis spectroscopy, where you can see we got different peaks, absorption peaks, which corresponds to different chiralities. We got something like 30 chiralities in the sample. Now, we separated the carbon nanotubes using the procedure developed originally by Catora, which is shell permeation chromatography, and we achieved a pretty nice purity, more or less 90% for the 7.3 chirality. The only problem is that the original procedure involves two steps. So two paths, multiple paths, depends on the purity that you want to achieve. Now, if you're trying to use chirality-separated carbon nanotubes for device applications, you gotta minimize the loss of materials, right? So we modified the procedure, and we managed to get a single chirality in one single pass. This is the first column of the chromatographic step, and we can see that we got two chirality. When we switch to the third column, we got just one chirality, and this is obtained in one shot, one pass. So the material loss is minimized. This is confirmed even from the PL spectra. Now, what happens when we put in a dye-sensitized solar cell? First thing to do, since we use the thin films, is to characterize the electrical conductivity. One important thing, you can see that, of course, the mixed chirality got a better electronic conductivity for the simple reason that there are metallic tubes inside. But single chirality conducts better than bundles of different chirality, because there are no Schottky barrier at the interjunction between tubes and tubes. So what happens when we put into a DSSC? First thing, you can see that the shunt is pretty bad. So the shunt resistance is pretty low. Why? Because the carbon nanotubes are exposed to the electrolyte, and as we said before, there is a catalytic effect for the recombination with the electrolyte for the reduction of the triiodide. But the shunt resistance increases as we reduce the amount of metallic tubes. You can see that the shunt resistance for the single Chirality is more than the shunt resistance for the mixed film. Another thing, the series resistance. So more or less the slope close by the on-circuit voltage. You can see that there are two contributes to the series resistance. First one is the one due to the conductivity of the different bundles of carbon nanotubes, so different chiralities. Another one is due to the contact between the FTO glass, the substrate, and the carbon nanotubes. The contact is not the best in the world. The adherence needs to be improved. But what about the work function of different carbon nanotubes? Look at the open circuit voltage. The open circuit voltage now, when we create an heterojunction between carbon nanotubes and titanium dioxide, the Fermi level of titanium dioxide shifts down. So it means that in theory, the open circuit voltage of the cell, because the open circuit voltage is the difference between the Fermi level of titanium dioxide and the redox potential of the electrolyte, is supposed to decrease. But don't forget that we introduce an heterojunction, so we introduce a Schottky barrier height, so it means that there is a push forward for the electrons, so it means that the saturation dark current is less, the recombination is less, and so the open circuit voltage is more. In fact, single chirality, which means that we are tuning in the right way the work function of the material of the carbon nanotubes, show a better open circuit voltage. Another thing about the short circuit current, we say that we shift down the Fermi level of titanium dioxide, which means that we shift down the titanium dioxide conduction band. So it means that there is a driving force for the electrons to be injected from the lume of the dye to the titanium dioxide conduction band. So even the short circuit current and the quantum efficiency, of course, are increased by the single chirality. Then we measured the Schottky barrier height, and you can see that there is a proportion between the efficiency of the cells and the Schottky barrier height. The Schottky barrier height is measured by the dark current of the cells. Now we have seen, since the shunt resistance of the carbon nanotubes is so low, it means that they can catalyze the recombination with the electrolyte. So it means that if we use them as a counter electrode, they are supposed to work fine. In fact, what we did, we compared the standard platinum cell with the platinum counter electrode with mixed carbon nanotubes with a single chirality. And we have seen that the main problem is that, of course, there are no metallic tubes in the single chirality, and there are less metallic species in the mixed tubes. So the series resistance of the cell is going to increase. And the electron transfer between the counter electrode and the electrolyte is going to decrease. So it means that the dominant recombination mechanism becomes the recapture of the electron from the dye. And so you can see that the quantum efficiency decreases. So, conclusions. First, we managed to separate a single chirality 6.5 and 7.3 in a single shot with one chromatographic pass. And it's promising for applications, I guess. Second one, we identified that there are problems with the series resistance due to the contacts. Second one, that we gotta protect the carbon nanotubes by the electrolyte, shield them by the electrolyte. Fourth is that there is an increase of the efficiency and other photovoltaics parameters due to the single chirality, for the reason that we explained before. And last one is that we can use as a counter electrode a film of purified metallic tubes to decrease the series resistance of the cell. This is for the Dye-Sensitized solar cell part. What about future work? Future work, of course, we gotta protect the carbon nanotubes for the electrolyte, for example, with the blocking layer of titanium dioxide obtained by spray pyrolysis. We gotta use impedance characterization to discriminate a different mechanism of the cell that involves single chirality carbon nanotubes. And we gotta try to separate metallic tubes to use them as a counter electrode. This is for the Gretzel cell for DSSC. What about if we want to extend this approach to other cells? First, we gotta measure the work function and applying it to different kind of materials. Second, we gotta find a way to get rid of the SDS, which is the surfactant used for the separation of the tubes, because there is sodium inside. The sodium is no good in every kind of photovoltaic device. Third, we can try to apply this concept to a new device, an emerging device, which, needless to say, are the perovskite cells. Everybody knows the evolution of perovskite cells from the synthesized approach to the PIN structure. The advantage of the structure here, the last one, is that the temperature of the processing of the thermal treatment is very low. So if you need to use carbon nanotubes, it means that your thermal treatment temperature needs to be low. There is the Kulkarni group from Singapore that they use carbon nanotubes for bifacial perovskite solar cells. Now, it's a promising approach because you can get light and current generation from both sides. And of course, it's cheaper than silicon bifacial solar cells. The problems they encountered are the sheet resistance of the carbon nanotubes film, the optical transmittance of the carbon nanotubes film, and the driving force for the holes to be injected from the perovskite into the carbon nanotubes. So we thought that our approach, using different Wolf action, using different absorption peak, and using different conductivity by a single chirality carbon nanotubes, can be even useful for those kind of cells, for bifacial perovskite solar cells. So, thank you to everybody, and from Professor Tagliaferro from Torino, and thank you to you. Okay?
Thank you, Simone, for the presentation. So we have time for questions. Okay.
Sure.
Can you show back your graph of the random spectra?
Yeah. Yeah.
So you have a one spectra.
Yep.
You get 2,500 more.
That's the splitting of the G and D band. Because when you got semiconducting tubes, you have the splitting of the G band in plus and minus and D band in plus and minus. So it gives you the degree of order and disorder of the structure. We made the proportion and we saw that the D to G ratio is something like 0.09, so it means that our very ordinate structure with big order, with large order. Those. That's it. D, G.
And another question. You said that the conductivity of the
Yep. Yeah, we are.
Is that because you have metallic tubes?
Yeah, for the mixed chirality, the conductivity it's higher, so the sheet resistance is less because you have metallic tubes. Here we don't have metallic tubes because they are purified by the chromatographic procedure, and you just have two different chiralities that have a junction between them. Here you have the same problem, so you don't have metallic tubes, but you have a single chirality. So you don't have a barrier at the interface between the two kind of different carbon nanotubes.
Questions? Please. Okay, I got a question. So why do you call short barrier with the wall?
Yeah.
What's the difference in the normal?
Let's see that when you have carbon nanotubes and gallium dioxide, in theory you have a junction between two semiconductors,
Okay.
or a junction between a semiconductor and a metal, depends which kind of carbon nanotubes you have. Now, Schottky barrier is a general term because even studying heterojunction, you can still use the term Schottky barrier height. There is the approach developed by Turtsov that shows that the Schottky barrier concept still stands even for heterojunction. But strictly speaking, a Schottky barrier is just a barrier between semiconductor and metal. So in theory, just if we have metallic tubes, or if we have multi-walled carbon nanotubes, we could call it Schottky barrier.
Okay, thank you.
Oh, no.
Questions? Thank you very much.